Hello. Today I'm going to explore one topic in particular, and yeah, the main selling point is that you'll have a consistent way for talking about the idea of very big. And for this entire talk, big N and epsilon, which is 1 over n, are going to represent the same number for every slide, specifically some infinitely large integer, and I'll explain what infinitely large means, but for now, really just think of it like any other number that's just, it's bigger than 1, it's bigger than 2, it's bigger than 3, and all the normal numbers. And then epsilon is smaller than 1, it's smaller than a half, a third, aka infinitesimal. So what does this concept of an infinitely big number buy us? Well, here's one thing. A somewhat simplified derivation of the Taylor series for e to the x, starting with the definition from continuous compound interest, where the rate in the compounding would be the x at the very top left, and then n is the number of compounding periods. The usual way this is set up is you take a limit as n, the number of periods grows and grows, and you'd end up with e to the x. But we're going to do it in a different way. So the color coding, the red means that first we just get rid of this limit, we just drop it. Instead, we allow this n to just be the n I'd talked about, an infinitely large positive integer. Okay, now that I've done this is some massive polynomial with an infinitely large number of terms, but it is a polynomial. And using the binomial theorem, I can rewrite it. This bit in red of 1 to the power of n minus k, that bit is just 1 to the power of some integer and is therefore just 1, and multiplying by it doesn't affect anything, so we can drop the whole thing, leaving behind n choose k and x over n all to the power of k, which I just expand out in this line. The next step is to look for more stuff to cancel, because already you can kind of see the Taylor series.
Sorry to interrupt, Alok, but
hiding.
you might want to move to the side a little. Your head is in the way of the calculation.
Like in real life or in like
Your virtual head.
Yeah, I'll close the board out. There.
Yep.
Okay, perfect. Okay. So I cancel out just using definition of factorial part of this numerator and the whole of this denominator of n minus k factorial, which leaves behind n times n minus 1 times n minus 2, and so on from n minus k plus 1. So this whole top thing has exactly k terms. And now for where we use the fact that n is infinite in an essential way. I can rewrite this green bit divided by n over k as the red bit just below it, the nested product. And observe the note to the side. The idea is that since n is infinitely big, think of the intuitive expression in infinity minus 1 all divided by infinity, with the infinity supposed to represent the same quantity. It's infinitely close to 1. It is not quite 1, but it is infinitely close to it. And so we can just cancel the whole thing. For why that's a legit thing to do in more depth, we'll get into it. But now this is gone, leaving behind just this, which you can see is the classic formula. And if here I was using the fact that k is just a standard limited number, for k that counts up to some unlimited index, the expanding out the terms will give you that you're dividing some unlimited number by some unlimited number squared, and therefore that this whole expression is infinitesimal. That's what the squiggly 0 means, and can be dropped. And this is why I can just say, let this specific infinite number be the upper index that I'm counting. Like, why didn't I just use 2n or 4n or n to the power of 40? well, I could have, then it would make a difference for unlimited k, but the difference is infinitesimal. So that's why I write the squiggly in the blue boxed area for e to the x is the standard part of this unlimited sum. And if you write it to just include standard numbers, then it's equal to it. Okay. Questions? Was all of this familiar?
Not with this funny
Sort of.
sort of infinite n, no, but the limit form of that, yes.
Okay. So funny infinite n. Fair enough. How do I move it? Throughout this talk, I start on the more intuitive end and then build towards more formal definitions. The aim of this talk is more to give an idea for how to actually use this concept of an infinite number, because there are many resources online to look up the formal construction of them, and I'd be happy to talk about all of them in the later half. All right. Here is a picture of the implicit structure we're working with. The top line here that I boxed in blue just now. You guys do see that I'm boxing it, right?
Yep.
Okay, cool. So the real line that we're all familiar with is still there, but now it has these two additional bits attached to it. One is that in between all these standard points, there's a whole tiny copy of a line, in fact, for every single standard point. That's the pink bit. And each of these infinitesimal neighborhoods, which formally is the set of points that's infinitesimally far from a given one, and from the middle of these slides, you see a definition of infinitesimal is a number which is strictly less than 1 over k for k 1, 2, 3, and all standard numbers. I'm deliberately not really defining standard, and instead, here's a quiz that I'm going to give like probably about a minute, then I'm going to ask you guys to give answers for real. And I'll say don't think too deeply about it. And here, epsilon represents 1 over n represents some unlimited number, and this is 0.999 repeating. And this e is the one that's like 2.718, and this is just pi. So, is pi plus e standard? Anyone? Yes. Okay. Is epsilon minus 2 standard? Okay, it's 2 answers so far. I really like this thumbs up down thing. Okay. Is tangent of big N standard? Okay, one person gave a thumbs up to that. That is not true. That's not standard because N is not standard. Like if it was tangent of like 4, then it would be a standard expression. Basically because there's some expression here that involves basically a funny number, one that is not a standard limited real number. And I know that that's somewhat circular, but the idea really is that you can semantically identify whether something is standard. Okay. The last one is 1 minus 0.999 repeating standard. Gotten 1 so far. 2, 3, 4. Okay, everyone gave this. So I think you guys based on the thumbs up, do have at least the intuitive idea, for which I'm very glad. Let's turn our attention back to the very top line for a moment. Notice all the omegas, the W-looking thingies.
Sorry, before you go on, could you... I guess I sort of
Yeah.
intuitively get why the last one is not supposed to be standard, but it hinges, I guess, on what you mean by this expression, that just
I
subtracting.
had wondered if someone would bring that up, actually. This one, I was honestly just going to gauge people's responses. If someone asked that, I think they have the idea anyway, and the quiz fulfills its purpose. For this one, I guess, if I meant anything, it's to evoke that, no, it is really close to, but not quite one. I know that the notation has, like, there's ambiguity in that.
Yeah, that's interesting, though. Thanks.
Yeah. And thank you for bringing up that point. Okay. So
Hold on. So the last one is not 0. It is some epsilon because you've got a 0.99 repeating, like infinitely repeating,
Yeah.
or like big N repeating. Is that
Yeah.
true?
Big N repeating is more accurate. Yes.
But if I just have the normal, whatever that is, the normal 0.999, this should be 0, right? Not
Yes.
epsilon.
Yes.
Okay.
Good.
So it's actually minus epsilon. Is that right?
So this would be equal to epsilon.
This would be epsilon.
Yeah. Sorry. Excuse me. Yeah.
Yeah. Cool. And just as these numbers, the infinitesimal numbers are smaller than any standard number, the unlimited ones are, well, bigger. The sense in which they're, like I'd said in the title of the talk, infinite numbers that act like they're finite. Basically, the way in which they act like they're finite is that they really do just behave like ordinary numbers. For example, take that omega and omega over 2. Okay, here's a question. What's omega minus omega over 3? Where omega is some unlimited number.
2/3 omega?
Yes, exactly.
Uh-huh.
Whereas the usual notion, if you just say like infinity minus infinity, unless you know the expression that produced those infinities, that could be anything at all, and you usually would just call that undefined. But here, not only is it defined, you have a pretty precise answer. You're just doing arithmetic.
Do I have to be
Like,
scared
notice
of
that
omega squared, or is that just omega squared?
omega squared is just omega squared. Like the square root of omega squared is omega.
Okay.
So they really are behaving like standard numbers in all arithmetic ways. And in this case, you can even do a sort of induction where you can count down from omega all the way down to 0 or into the sort of standard initial segment.
Is there a difference between this and working with finite numbers and then taking the limit after you've performed your computation?
There's a way to compile all of this into statements about the standard real numbers. This was actually a bit later, but here's why, like the one-liner for why should you care about any of this? Because any first order statement about the real numbers is true if and only if it's true about these hyperreal numbers, which is a really broad class of statements. Like all the ones that are simple arithmetic are ones. For example, this implies that there are unlimited prime numbers, not just that there are infinitely many primes, which is kind of trivial, but that there's individual unlimited numbers which are prime. They have no finite factors, they have no infinite factors except for themselves, and well, I guess they have one as a finite factor too, but that's it. And there are also infinitely many of them because there's infinitely many primes.
Thanks. I will keep the faith and keep listening.
Cool. Extremely important point that will be hammered home in literally the next slide anyway, so let's just walk to it. Yeah. This line, "A world in every grain of sand," it's from a William Blake poem, and it's how I like to think of the
Sorry, Alok,
infinitesimal
I think you're
neighborhood.
standing in front of a different slide to the one you think.
Oh. Interesting. Yeah. Okay.
Yep.
There. now do you see? This bit is supposed to capture that, as you'd seen here, in this neighborhood, that's only really, it's the extent of a point. It's only 1 point wide, one standard point wide, but it contains a whole copy of the line. And you can just keep doing this. Like, say I picked this point right here. I'm going to do it in green. Like that point. I can zoom in by another factor, let's say of omega or something. And then I'm basically looking at an epsilon squared line. And then I can zoom in more to get an epsilon cubed, even tinier line point by point, and this never ends. And you can go the opposite direction too, with omega, omega squared, cubed, etc. Omega to the omega.
But then the squared has different properties than normal numbers.
The square root.
Like you're squaring epsilons to get these totally new lines. That's not a normal number thing.
They only share finitary properties with normal numbers, first order ones, properties that quantify only over elements of an individual set and not over subsets of some given set. That would be a second order property. And this property of like having a whole line attached, having some set attached to it, I think is a second order property. I will think more on that one though, so thanks for bringing it up. But I think that's a second order property and therefore would not be captured by this transfer principle. Keep in mind that first order logic and first order statements are quite broad and capture a lot of useful stuff. Like they can't capture a statement like the real numbers are complete, but these include the real numbers. And so they have a form of completeness that's good enough in practice because it's at least as fine as the regular one. Anyway, fact that these infinitesimal neighborhoods are disjoint gives two really nice things. One is if you prefer doing like to prove that A equals B by doing a bunch of algebraic manipulations and getting a whole chain of equalities to finally show that something does indeed equal B, versus an analysis, you usually prove that A equals B by showing that it's less than it, it's greater than it, and so you squeeze its value, which I've never liked doing. I don't like proving inequalities twice. I'd rather just do it with an equality. Here, this relationship of is infinitely close to does the heavy lifting. It's basically the equal sign of this sort of infinitely close approximation world. Does that make no sense? Okay. Someone's agreeing it makes no sense. That's two. Would someone like to venture a specific point of confusion?
My thumbs up was agreeing with you, not that it doesn't make sense.
Okay, cool. Another. This one will actually require saying stuff out loud. Because these neighborhoods are disjoint as well, you have the very important fact that every non-standard limited number, so say 1 minus epsilon, is infinitely close to at most one standard real number, and therefore can be uniquely rounded off to it, basically by dropping the epsilons, and that's called the standard part function. And you're going to compute it right now. What is the standard part of 2?
2.
Yes. Good. What is the standard part of that third expression where epsilon, the 77 minus 3 epsilon plus 2.7 epsilon cubed plus 1 minus epsilon all times epsilon to the power of n?
How many levels of inception do you want us to go up here?
78?
This one was me just sort of messing with you guys, to be honest. Yes, it's 77. The person who just like added the 1, I see what you did. I did that too the first time. But yeah, like the rabbit hole goes as deep as you're willing to make it go. Okay, last one. What is the standard part of n where n is unlimited?
0? I mean,
Zero.
well, there is no standard part.
Yes, it's not 0. This one is
Infinity.
part. Yeah, this is in the category of undefined. Like if like usually in practice you want your computation to end up with something limited. It's fine if it has a bunch of epsilons attached, but typically if you're carrying around some infinite term at the end of your computation, you've been doing something odd, which we're about to do right now. Here. We're going to differentiate a function twice, in fact, which is not even continuous to begin with. Specifically, the step function. This particular
Sorry, you need
instance
to
of the step
move
function.
over a little bit again, Alok.
Okay. I'm hiding behind my own slides.
It's all right. We don't bite.
Yeah. Okay, so the step function is 0 for negative inputs, 1 for positive inputs, and 1/2 at the point 0. And that curve in red I drew is what I call a hyperfine that should be approximation, or a hyperfinite approximation. But the point is that we model it with some function which is differentiable, which is infinitely close to it at all the standard points. And the one I picked is this. Any logistic curve would work. There are infinitely many possible ways to do this in general. Usually you just pick one that's convenient and has a nice functional form. So I went with something easy, just the basic logistic function, where n is unlimited. The multiplication by n that's highlighted in red here is basically where all the magic happens. So the table is a case analysis. If x, the first thing means that x is strictly positive and is not infinitesimal, also called appreciable.
Can I ask here, when you write
And-
e to the minus nx, what you mean is some kind of limit, I guess, unless you have a different definition of the exponential. So it's, or is it just the definition you gave
Like in
earlier?
here, the one I gave earlier.
And do I have to worry about that sum converging or something? Or like the standard part converges and I just don't worry about the other
An
part? Or?
unlimited sum of unlimited terms itself always exists. There's some saturation principle that guarantees this.
I see.
Okay, so for positive inputs, what will happen is, okay, plug in some standard positive number for x. Let's just say 2, because why not? Then we would take e to the power of negative 2n. N is unlimited, so this is basically like taking e to the negative infinity, which in this case is not exactly 0, but is arbitrarily close to it. So we'd end up with 1 divided by something that's really close to 1, which itself is infinitely close to 1. Like, this function is still strictly monotonically increasing, but all of the increases happening in the infinitesimal neighborhood is of 1. And again, the fact that infinitesimal neighborhoods are disjoint, all these points will round to 1 uniquely and to no other number. And in this way, this curve will just sort of snap onto the straight line. Similar will hold for the negative case, where then you'd end up with the same as this, except the sign flips. So you're dividing by 1 over something that's unlimited, basically 1 over n, and therefore infinitesimal, and therefore infinitely close to 0. The case of x equal to exactly 0, worth using this case to highlight a fact. 0 is the only number which is both a standard number and infinitesimal, and it's the smallest infinitesimal of all. Like if epsilon is an infinitesimal of order 1 and epsilon squared is order 2, infinity's order, I don't know, omega, just multiplying, sorry, 0 is order omega. Like multiplying by 0 will always just give you 0. So this would just be e to the 0, which is just 1, which catches that one standard point that we need in the very middle. And then what about all this stuff? This is the case in the middle of x is infinitely close to 0, so it's infinitesimal, but it's not exactly equal to 0. And the upshot is that it can just be, and it will just be this any value between 0 and 1. Here I evaluated it at the infinitesimal point 1 over n. So this simplifies to 1 over 1 plus 1 over e, which is about that, 0.73. If it was some other infinitesimal, like say 2 over n, I would get some other value. But basically these whole cloud of standard and or limited values, as soon as I take a standard part, the only one that will stay is the standard point at 0, which is a half. The rest will disappear. So I'm doing a bunch of funny stuff, but all the funny stuff is done in basically in the gaps between points. Questions, confusions?
So minus 1 over n is also infinitesimally close to 0,
Yes.
just from below.
Yeah. Yeah, being infinitely close is more of a close by magnitude.
Alok, look. Can I ask you a question? Is every function infinitely close to a continuous differentiable function defined on the hyperreals?
We continue. Like basically are they in space? How does that?
Yeah, is it like in the hyperreal world true that basically everything is just continuously differentiable?
I'll have to get back to you on that. It does definitely extend the class of differentiability, but I haven't looked into it deeply enough to have like strong words to say. Oh, there's the rest of it. All right.
How could that be true if the normal real numbers, I mean, they should behave like they used to inside this bigger class, right? So you have in mind this kind of, these universes like in Topoi where somehow for some reason everything is continuous, but that's to do with the restricting the class of functions in some way, right?
No. It's much more mundane than that. I just mean if you have any non-differentiable function or non-continuous function on the reals, you can extend that to the hyperreals and then find a what is this? You can find a function that is infinitely close to your original function, which is continuously differentiable.
Yeah,
Just like
so I think you just get that from Stone-Weierstrass, or the sort of transfer of that. Because like the statement that the rationals are dense in the reals, you could say that it's star extension, so the hyperrationals, lovely name that, is every real number is infinitely close to some hyperrational number. Like not necessarily to some rational number, but a hyperrational one, because standard points can't be infinitely close. This is why the idea of infinitely close and being able to cut things into a grid with an unlimited, like a specific unlimited number of pieces, like n, is useful because it lets you implement this idea of the number next to another number, even though there is no such thing really. Certainly not in the standard reals, because if two numbers are different, then whatever distance they're separated by, you can just keep dividing it in two. But here, this hyperfinite mesh, this unlimited mesh will just catch everything. Anyway, I had promised differentiating the function, not just modeling it, and here are its derivatives. The first is just the function itself, the logistic one. The definition of the derivative is basically the same, except now epsilon is a literally infinitely small number. And plugging in our function, we got these two functional forms, which are kind of a mess. A better way to think of them, I think. So on the bottom right picture, the one on the left, that's supposed to be the Dirac delta. The idea being, it looks like a normal distribution whose variance is infinitesimal, or standard deviation is infinitesimal. So outside an infinitesimal neighborhood of 0, it collapses to being infinitesimal and therefore would round to 0. And in the infinitesimal neighborhood of 0, it has an unlimited height. This specific function, if you plug in 0, I think you get that its height at 0 is exactly n over 4. So it's some infinite number divided by 4 at 0, which is satisfying in a weird way. Differentiating that again, you get the dipole moment, sort of how you'd model an idealized tiny magnet. And you can just keep differentiating them. I did it in Wolfram Alpha, and they look kind of like flowers, and you have the function, so I encourage you to try it out. It's pretty fun. Just write these and then just say where n equals like 10 to the 6 or some big-ish number, that, and then you'll get results that look like this. Cool. Questions?
Where did the epsilon go? Or is it 1 over n?
It's the specific epsilon. That's why I put at the very first slide that I meant literally the same one. Like in the usual setup of a function that's supposed to be standard, then you would add a standard part because you're trying to assert that it doesn't matter which epsilon is picked. Here, I guess it doesn't matter actually. For functions like these, which are not functions in the usual standard world, because there isn't really the vocabulary to coherently talk about them, at least not without introducing a bunch of technical machinery like distributions.
I have a question. So physicists care a lot about the direct distribution and also derivatives of that.
Yeah.
And it works sort of, it seems kind of similar to this. But the issue they complain about is that you can't multiply these distributions in a good way.
There is no in general way to just multiply these that's just canonical. People, I think, just pick out convenient function classes. There is a paper on using hyperreals for exactly this. I think that's like, I can send you a link to it later. They use the phrase Colombo algebra, I think, to refer to what formalism they're trying to emulate with the hyperreals, but it's easier.
So are you saying that if I take these hyperreal functions, like the derivative, the Dirac, and these things, if I multiply them, it doesn't preserve the representative? It's like doesn't work well with multiplication? Is that the case?
It depends on the function. Some of them will work fine. Others, like you can't extend it in a nice way for every function. So you end up making concessions to the classes. I think coming at this from distribution theory and functional analysis is actually Grothendieck's first bit of research around nuclear spaces and stuff, which then led to his later work. But that's getting kind of far afield. So I'd like to get back to this one. Here are some examples of infinitesimals that you probably have seen just like behind the hood maybe. The top right one is a picture taken from Euclid's Elements actually. And
The right?
yeah, the top right. That's the
Can you
angle.
move your character a little bit? We can't see the board.
Sorry, say that again.
You have to move to your left a little bit to the next slide for the Orbcam. Yeah. Sorry, the other way.
Here.
A bit too far. There is good. Yeah.
If you could see the janky stuff I'm doing right now. Excuse me, I'm stuck in Roblox. Fine, there. I hope I'm not blocking it. Okay, do you see clearly?
Yep, that's fine.
Okay. So that angle that's formed by F, A, and E, that's called a horn angle. And the idea being it's an angle smaller than any angle, but it's still there and it's not quite zero. I think it's called a horn angle because horns curve like that and come to a point. Here now we can just say that, okay, there's an angle and it's infinitesimal. It's epsilon, why not? Something small. Then the second thing, you have a closed unit interval and you just throw a dart. What's the probability of hitting the number, exactly hitting the number 0.3? This is a question.
Epsilon.
Nice. Yeah, you really anticipated it. Yes, epsilon. The idea being that, yeah, you would, so each of these points have a tiny line around them. Okay, well, that's good. We can cut this whole thing up into infinitesimal intervals. And then,
But wait,
We've
why is it
taken
this epsilon and not 1 over m for some other m like n?
it could be. That's why doing things like this is, like, all of them will round to the probability being 0 in the standard sense, because all the probabilities that are assigned to any interval containing a standard point, no matter what you make it, will still be infinitesimal. So yeah, it well could be 2 epsilon or
But
epsilon to the 4.
can I make
or
a
something.
critique then? Maybe this is unfair, but
Yeah.
so say generalized functions or distributions is a way of layering some more general theory on top of normal functions in a way that accommodates derivatives of Dirac deltas and so on. And it's maybe artificial, but at the end of the day, we care about the numbers we get out by adopting this artificial ambient theory of the infinite. And you're arguing that hyperreals are somehow better because they do away with that somewhat artificial surrounding ambient stuff and are sort of more direct.
But there's still this ambient surrounding thing,
Right.
which is pulling these numbers from the void.
Yeah, and it's just like, are you just kind of just replacing one set of baggage with a different set of baggage? And in that case, why is it somehow better?
I would argue that the sort of meta reason that I like these so much and think that they're better is that I see them as the next step, natural step in the enlargement of the idea of numbers. Like, we all start with not even the full set of naturals, just 1, 2, 3 to begin with. And then at some point you realize you can just keep adding 1. Then you get to confront the idea of infinity. At some point 0 is introduced, then negatives. Usually fractions have already been introduced at this point, but then if you want to take a square root, you need irrationals. And then if you want to solve algebraic equations, you need complex numbers. Here, if you want to distinguish scenarios like these, you need infinitely small and large numbers. And each one is a clean enlargement of the other. Like, the typical upshot of how you actually use these in practice and why the arbitrariness of them in most scenarios is not actually a problem is that for scenarios that do have some standard interpretation, then there will be an independence from which particular infinite or infinitesimal number is picked. In non-standard scenarios, there is more choosing, but to my understanding, that happens in the ambient standard theory as well. This one allows us to draw much more strongly on intuitions about numbers, which are maybe like the strongest mathematical intuitions of all, except for like basic geometry and shapes. I don't know if that's a very satisfying answer.
It also lets us swap limits, right? Like, that's something we couldn't do before with derivatives.
Like, it gives more sequences a limit, including plenty that weren't convergent before. That's like here, you can compile all of these hyperreal numbers into infinite sequences of real numbers. And that's not especially constructive, but the reals themselves are not really computable either. So I don't worry too much about that.
I feel like the transfer principle is doing a lot of heavy lifting for you conceptually. Would that be accurate? I mean, when I think about this, and I guess I am to some degree convinced this is a useful way of thinking about it, the role of the transfer principle and first order logic here seems to be both a blessing and a curse. It's a blessing in that some sense you can't say, at least if you restrict to first order logic, these are as good as the real numbers you think you like.
I think of it like this. Like, okay, say this green box is just this whole standard mathematical universe, like sets, functions, points, all that. Bunch of arrows for all of them. Okay, and now you create this hyper thingy, which gives you all this extra room. But there's also this intermediate region where transfer carries. Stuff, the kind of questions that live out in the boundaries of this fuzzily drawn analogy are like, if I just give you two unlimited numbers just out of the void, like A and B, with no further information, a question like, is A odd or even? Is it greater than B? Basically any question at all, except that it's bigger than any standard number, can't be answered. It doesn't really carry any information other than the fact that it's big, and it's kind of a placeholder for big. However, that's only in the purely external realm. Things that stay within this first order realm will transfer in a unique way, and this outer realm is basically where research in the overall field happens. I think the people who tend to use this in practice are people who work in differential equations. Terence Tao uses it a lot, and ultrafinitists. Ultrafinitists, a weirdly large amount of them like this. I think because it sort of discretizes the continuum. Okay. In fact, as an example of this discretization, I'd like you to turn your attention to the two circles on the bottom right. Well, polygon and circle looking thing. This is to illustrate a concept that's called hyperfinite approximation, where, okay, as a basic principle, given some smooth curve, you can imagine it being made, okay, there's a bunch of points, but now replace the point with an infinitesimal line around it. And now this curve has become some infinitesimal chain with an unlimited number of links. And is therefore, well, it's not a polygon because it hasn't closed up, but it is made of lines. And this circle, if I just cut it, every point on it is an infinitely small line. In total, it will have some unlimited number of lines. Like, here's one sense in which those numbers are not arbitrary. We touched on this earlier, but I'll make this more explicit. Say that the number of points to identify the number of sides of this circle is some unlimited number C. Then a circle that had twice the radius, which is also an infinite circle, keep in mind, because the radius of this would be what? It's like 2 pi r equals C. So this would be C over 2 pi. So this radius is also unlimited. But anyway, a circle with twice the radius would have 2C many side pieces, possibly plus or minus 1. There might be some round off. And so, like, one of these numbers, you do end up making up a name out of the void, but typically it's links to other quantities that are unlimited, are not arbitrary, and you can write those down. And given those relations, you do have a proper sizing for the infinities, except for the first one that was introduced. So that sort of makes sense. Okay.
Yeah, I have a question about this example, but maybe I can save it until the end. Or do you have more to say, or you want to finish there?
No, I decided to leave it enough time for questions, so I'm pretty satisfied. This gives like 15 minutes, so fire away.
Great. Yeah, I'm quite interested in this final example you gave because, well, given you mentioned Euclid, so the left-hand example, I guess in modern day we'd think of it as being just that set of points or perhaps the set of lines, but Euclid would have thought of it as a construction. And the analogy between constructions and programs and proofs, of course, goes back to Euclid. So you could think of that that polygon is actually the construction that produces it as a sequence of deductions in Euclid's axioms. But then I wonder, is there such a thing as a hyperfinite proof? Right, I mean, the construction of the right-hand side is in some sense a limit of the constructions on the left-hand side. Is there like a developed theory of hyperfinite proofs?
Like taking some finite quantity and I'm not quite.
Not quantity, I mean constructions. So Euclid doesn't think of the polygon as, I mean, he doesn't think of numbers, right? He thinks of the construction. So, and the construction is like an algorithm. So I'm kind of asking, have people in computer science picked up
like a hyperfinite algorithm.
Yeah.
The closest I've seen is that Nick Bostrom seems to know this stuff because he mentions the use of hyperfinite numbers for infinite ethics if the universe is actually a fair number of this too. Sylvia Venmakers is one in particular. But is there any computer?
So there's
Yeah.
can I make a couple of remarks on this?
Yeah.
So one thing is, if you make models of these hyperreals, it uses ultrafilters, so it uses a weak form of the axiom of choice. So that makes it all extremely kind of problematic a little bit from like actual constructing things. There are also syntactic approaches where you don't do that, but yeah, this is sort of an issue. There is an existing theory of constructive hyperreals. I'm not sure. This is quite subtle because if you
That's
just do it naively. No, I understand, but
the closest I know of for hyperfinite proof, I think these proofs are doing essentially the same thing, but they're not using this formalism. Proving like some property. Like I'd read this in the context of finding mass gaps. So this I'm not speaking with authority, and you really should just like Google this one. But they say that they prove that at some finite numbers the problem is undecidable, and the way they prove it is by proving it at infinity, and that there's some transfer. And the way they're talking about it, there being these increasing sequences of finite numbers, gives the whole thing of similar feels. I think if you saw it, you'd be able to suss it out. I can send you a link.
Yeah, thanks. I'll ask you about that later.
I don't know if anyone in computer science has done anything with it. Closest I know is like Dan Roy and House Duan who have used it in statistics, especially Bayes statistics.
I mean, I guess to put some red meat in front of Alexander, it makes you wonder if there's like a hyperfinite version of the theory of linear orders that contains a model of cyclic orders. That would be the topos theory version of
you mean like
that.
sort of how you're thinking of like the integers as the cyclic group as kind of being linear too, but also cyclic in a way, or is this unrelated?
Yeah, I'm not sure. I think I'll open the floor for other people to ask questions rather than hog you for the next 10 minutes. Other questions for Alok?
Yeah. Also, if people want more examples, I can give them.
While other people are thinking, I'll ask another one. So what got you into this cult, slash system of beliefs? It feels a bit to me like the geometric algebra community.
I think the main reason being like the concept
Alok is also into geometric algebra, right?
Yes, I know.
Yeah, he knows well. That's the first time we had met, was talking about a paper that him and James Clift had done on in this vein. The way it unifies discrete and continuous, the theme of enlarging number systems, which is one of my favorite things about math, because the concept of a number compresses so much information. The really elementary way you can work with things. I love that you can just do the most naive sounding thing of just draw an infinitely big box. You can literally just say that, and that's totally rigorous, and it just works. And that so many statements about sequences that are awkward just become these nice idealized things. And then, unlike most cults, most cults don't have a transfer principle.
that's an awesome
If
line.
you ontologically accept the reals, at least up to finitary statements about them, you're sort of compelled to, if not accept these, then not like totally dismiss them. They have because of the if and only if, which is also not obvious.
Yeah, I would agree with that.
They also give a sort of different view of infinity that's closer in line with people's intuitions of a part-whole relation. Like, for example, if you had an open versus a closed square with or without the boundary, you could say that by some infinitesimal amount, the closed square is strictly larger than the open one, in the theme of not throwing away information, basically.
You also told me about radically elementary probability theory.
Oh, right. Yeah. There's this probability theory book that uses this stuff. Not even very much of it. It really only uses the concepts of infinitely large and small, and that's it. And it covers in just 80 pages like 3 times more probability theory than I've done in my whole life.
Yeah, I have to admit I'm a little skeptical of that. It probably is just more or less the same as skating over the details, rather than using a radically simpler, rigorous formalism. Is that a rigorous treatment? I'm okay with a not so rigorous treatment of elementary probability, but maybe a bit of false advertising.
He sets up the whole formalism in Appendix A. He says that he wrote the appendix to be self-destructing. Everything in it is rigorous. His arguments for them is sometimes a little rushed, that's for sure. Like, it's not easy reading. But even if it was fully expanded out, I think it would still be under 200 pages, like, safely. And does cover quite a lot of material. Like, it gets deep into stochastic processes, and there's another book on stochastic calculus that uses it as well. And I've taken a look at that one. The real benefits are that you don't need measure theory, because now the only event that has probability 0 is the empty event, which is impossible to condition on, because it can't happen. And that alone eliminates so many problems. Like, just, it's fine if you divide by like 5 epsilon. Also, measuring things becomes just counting again. Like, you can define a generalized measure. It's just a weighted counting scheme. And it also lets you treat discrete and continuous at the same time, and that book does so as well. Where a continuous distribution is a, quote, finite distribution by using this idea of a hyperfinite set. Counting combinatorics. What does that mean? Yo, what does counting combinatorics mean? Someone just wrote that.
I'm not sure, but I have another question.
Yeah.
So in linear logic, there's also a very important role for the different kinds of infinite. So an infinite that is sort of potential and only realized through interaction, in the sense that an unlimited supply of something is like a box you can keep drawing from and it never runs out, but it's not infinitely large in some sense.
Got it.
So do you see any, I mean, okay, yeah. So that's an important idea in linear logic. Is there something like that here?
Is there another infinity in linear logic?
Like, is there an actual infinity in linear logic as well, not just the potential?
Semantically, yes, but that's part of the tricky part of trying to understand what the content of linear logic is mathematically. So I think that's a hard question to answer.
Okay.
But it's not
like of something like this idea of something, well, not being limited, that you have as much as you want, but it's ultimately some finite amount. It's just bigger than any other number you had named before and whatever you're talking about. And if it's some first order thing, you can quantify over the elements you're talking about and just pick something bigger than all of them and all possible combinations of them up to some finite depth of symbols or something. Basically through compactness theorem.
Yeah, the reason I ask is there's some very similar kind of flavor to some part of that, but I don't know how to say anything more precise. So yeah, maybe it's a vague question, but I find it very interesting. I mean, this trying to put some mathematical detail on this potential infinite is what makes linear logic kind of interesting. So
I'm
And
glad
it's
you
not-
said vague, because
sorry.
one thing that sort of intuitively that they try to capture is a vague property. Like one example I thought about on a car ride is how there are many forms of cancer. Like the ultimate number of forms that can happen is sort of limited by the discreteness of the universe, but is essentially some infinite quantity, but it's also a vague one. And that's the kind of thing that I would model as an unlimited quantity.
That's an awesome note to end on, I think. Unlimited cancer. Okay,
Unlimited,
so
unlimited different fixes.
with unlimited
variety.
different fixes. Okay, yeah, very good. That's a better way to end. Okay,
Alex
thanks
had some
everyone.
ideas of a game,
Oops.
and you should ask
Sorry,
him
go on.
later. Thanks everyone for coming and for listening. I hope you learned something about infinitely big numbers.